All right, good morning, everybody. At the end of the last lecture, we finished talking about the bitwise operations, right? So we know how to left shift and right shift and compute bitwise and, or, XOR, and not. So today I just want to show you quickly an example of why you might want to do this in a real program. And the example I'm using today is for encoding color values. All right, so if you don't know this already, the most common color model used for displaying digital images, not just displaying, but displaying and representing digital images, is something called RGB. So in the 24-bit RGB model, a color is just a triplet of three numbers. So I'm going to use unsigned integer values, but they don't have to be integers. They can be floating point values. And so you use three unsigned integer values. In the most commonly used RGB model, they're 8 bits, right? So values between 0 and 255 inclusive. One of the values corresponds to the amount of red, the middle value corresponds to the amount of green, and the third value corresponds to the amount of blue that's in the color. And so that little table there just shows you some examples of some common colors and their RGB encodings. Right, so black is 0, 0, and 0, so there's no red, no green, no blue. White is 255, 255, and 255, so it's all red, all green, all blue, or the maximum amount of red, green, and blue. A shade of gray has equal values of R, G, and B. The lower the value, the darker the shade of gray. And then when you try to get colors in between, or you try to get other colors that are not necessarily close to red, green, and blue, they have some unusual color encoding or some non-intuitive color encoding. Right, but the idea here is that they're three 8-bit unsigned integer values. Okay, so why only 8 bits? And so the answer is not every, you can have RGB representations that use more than 8 bits, but 8 or less actually as well. 8 is the most common because it's the number of colors that can be displayed by affordable hardware. Right? And so most modern televisions now, I guess, is that true? Most modern televisions and high-end monitors can now do 10-bit color, but 8-bit still by far the most common. 10-bit color and 12-bit color would be, so some video games use them, some photographic applications use them, some medical applications use 10 and 12-bit colors as well. There's another form of RGB called RGB alpha, so it has a fourth 8-bit number. Alpha corresponds to how opaque the color is, or how transparent the color is. Okay, so if you have an RGBA color, you can represent it using 4 8-bit integers. So in C, you can write uint8 underscore t if you include types.h, and that gives you an unsigned 8-bit integer value. So I'm going to use that for today's example. And then you can store the individual color components of a color. So the color 255, 127, 63 with an alpha value of 31, you can store in 4 8-bit integer numbers. On the right-hand side, that's the binary representation of each value. Okay, so instead of storing them in 4 separate 8-bit numbers, you can pack the 4 numbers into a single 32-bit int. Right? The reason you want to do this is because on most modern computers, a modern computer wants to pass around data in chunks of 64 bits. So in other words, it doesn't want to pass around data in chunks of 8 bits. So if you passed in just the so if you wanted to pass in this color, rather than passing in 4 separate 8-bit numbers, it's probably more efficient to pass in a single 32-bit int. Right, and this is just a consequence of how modern computers are built, right? The underlying architecture of a CPU. So if you pack the 4 8-bit numbers into a single 32-bit, so perhaps by writing the red component in the upper 8 bits, right? Then the green in the next 8, and the blue in the next 8, and the alpha in the lower 8 bits. You can also flip them around, so alpha comes first. That's also common. So alpha RGB, alpha BGR is also common. Right, there's no standard format for this for doing this sort of thing. So you can pack these all into a single 32-bit integer, and doing so is not hard to do once you know the bitwise operations. Right. So in other words, if you start out with these 4 numbers here, you can easily construct a single 32-bit int. Right. So if you have a 32-bit int C, you set its value to 0. Right. I claim you can easily put the 4 values of RGB and A into C. right? So you start out with the number 0, right? That has, and the unsigned 0 has all zeros in its, as its bits, right? You take the red amount, right? So remember, red is all ones, right? 8 ones, right? Now the problem is you have 8 ones and you have a 32-bit number. So in order to get the 8 ones into a 32-bit number, you need to take your 8 ones and you need to shift them. Oops, sorry. You want to shift them 24 bits to the left, right? So remember, you have all ones here. If I shift all the ones 32 bits to the left, right, we end up over here, right? And we've now positioned our red bits in the leftmost, or in the most significant bits of C, right? Now I now need to combine these two numbers, right? And so to combine these two numbers, you can use a bitwise OR, right? So you bitwise OR all of these. Everywhere there's a 1 in either one of the numbers, you get a 1, right? Anywhere there's a 0 in both numbers, you get a 0. And so that puts the 8 bits of red into the upper 8 bits of C. And now you just do the same thing for green and blue, right? So for green, you shift it 16 bits to the left to get that, right? You now take the OR with C, which has its upper 8 bits as red, encoding the red value, right? You take the OR and now you get the red and green bits in the upper 16 bits. And you do the same thing with blue and the same thing with alpha, right? And so there's how you go from 4 8-bit numbers to a single 32-bit number representing all the colors. Sorry, representing all the color channels. Okay, so how do you get the individual 8 bits back out, right? So I just sent all the 4 color channels in one int. If I want to extract the red, green, or blue components, you can do a similar thing, right? So if I want to get the red component, right, all you do is you take C and you just shift it 24 bits to the right, right? When you shift C 24 bits to the right, all of these bits here fall off the end of the number, right? And the red bits end up in our lower 8 bits of the shifted value, right? To get the green component, right, it's a little more complicated, right? So the green component's here. Oh, sorry. The green component's here, right? So if I shift this number, so when I shift this so that it ends up over here, that's shifting 16 bits to the right, right? The problem is I've got all these red bits up here, which I don't want anymore, right? So to get rid of these red bits, I can take these two numbers and take the bitwise AND, right? I make a mask that's ones over here, right? So it's got 8 ones in the rightmost 8 bits, right? And I can take the bitwise AND, right? And that selects the rightmost bits of the shifted number, which is the green color, right? And so this is the using a mask and bitwise AND trick that I showed you in the previous lecture, right? So that selects, by having the masked bits, the 8 rightmost bits of the mask be all ones, that lets me select only the right 8 most bits of the shifted number, right? You do the same thing with blue, right? So shift, if I want these bits here, shift 8 bits to the right. That produces this number here, right? Create a mask. That's equal to 255, so it's an easy mask to create, right? Take the bitwise and that selects the blue bits here. And you can do the same thing for alpha, right? So for alpha, just make a mask equal to 255, take the bitwise and of the two numbers, and that selects the alpha component there, right? And so there's an example of when you might want to, or when you might need to use the bitwise operators. This is not uncommon if you're working with a graphics API like OpenGL or Vulkan or something like that. In those APIs, they often want colors. They can take the colors as 4 separate components, but it's faster if you pack them into a 32-bit. And you can do similar things as well. So many programs have configuration options, things that are true or false, right? And some programs have lots and lots and lots and lots of options, right? So rather than storing every option as a Boolean value, you can just store it as a bit in an unsigned number, right? And then you can use the bitwise operations to look at the individual bits to determine whether or not an option is on or off, right? So that's also extremely common, especially in the embedded world, right? All right, so there's just a little example, I guess a 10-minute example of using the bitwise operator. Right, that's about as complicated an example as you should expect to see in this course. If you look at the references that I mentioned in the previous class, I don't have them, oh wait, they're in the notebook. Do I still have that notebook open? Bitwise. Okay, if you look at these two references here, you will find extremely complicated examples of bitwise operations that can be used to perform all sorts of surprising tasks, right? It's kind of surprising that just by flipping bits or combining them with one of the bitwise operators or shifting them around, you can actually perform some very unusually complicated calculations. Right? I guess the other thing to point out is that the bitwise operations are typically very fast on a modern CPU. So you might want to consider the bitwise operations if you need to do something extremely fast for your application. All right, so that's it for the bitwise operators, and that finishes that notebook there. I guess the next notebook is the floats notebook, but there really isn't much to say about floating point numbers. They work exactly the same as they work in Java, right? So there's a float, there's a double, and there's a long double. We're never going to use long double in this course. On most modern architectures, long double is the same as double anyway. In principle, long double is a 128-bit float. But most modern computers, I believe most modern computers do not is that true? I'm not sure if they natively support this or not. So even though you're using long double, you may not get full CPU support from them. I'm not sure if that's true or not. Double certainly has full support on a modern CPU. So does float. Okay, so the only notable things to mention about the floating point numbers is that there's a header called math.h, and this defines many of the mathematical functions that you might want to use, right? So things like square root, calculating an exponent, the trigonometric functions and things like that, they're all defined in math.h. They're pretty similar to how the functions work or how the methods work in java.lang.math. The notable exception is that C doesn't have name overloading or method overloading. So the functions that correspond to the different types have funny names. So for example, the trigonometric functions, there are 3 variations of the trigonometric function, right? There's a sine f. The f here indicates that it takes in a float as its argument, right? Regular plain old sine takes in a double as its argument, and sine L takes in a long double as its argument. Right. So there's no function overloading in C, so the names all have to be different. So that's why there's a sine F, sine, and sine L. Right. Using the functions, they work exactly the way you'd expect them to work. So I'm not going to bother talking about how to use them. The only other notable thing to talk about is printf. So if you want to print a floating point number, printf is the function that you probably want to use. The conversion that you want to use is just f. So this works for all of the floating point numbers if you're going to print them. If you want to control how many digits to print after the decimal point, you use a decimal point after the f, and then the number of digits of precision, right? So the number of digits of precision is the number of digits after the decimal point. So right here, if you don't specify the number of digits, you get 6 digits of precision. So %.12f gives you, prints out a floating point number using 12 digits of precision. So 12 digits, oh, sorry. What's the problem here? Symbol lookup, blah, 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 pow. Now, what do I have to do? I forget what I have to do to get this to work now. This is complaining because it's not linking to the math library. And so pow needs the link to the math library. I forget how I don't remember how to fix this off right at this moment. Anyway, it's fine. So when you print out the square root of 2, that 12 is the number of digits after the decimal point. If you, in front of the decimal point, you can specify the minimum number of characters to use in the output. So if you say something like 20, and run that again, this number here, or that value there, will be printed out using at least 20 characters, right? If the number of digits is less than 20, then it pads the number in the front using spaces. So in this case, there are 12 digits after the decimal point, 13 including the decimal, 14 including the 1, and then 6 spaces here in front of the 1 to get to 20. This is the minimum width, so if you specify 0, that doesn't do anything in this case, right? the minimum number of characters to print, it'll use zero characters as the minimum number of characters to print, but it needs more than the minimum to print out that number, the number with 12 digits of precision. So it just prints out that value there. And that's all there really is to say about floating point numbers, right? You guys know the rest of it from Java. Okay, so that takes us to the pointer notebook. And so this is the really, I guess this, besides the bitwise operations, this is where things really look different compared to Java and Python. All right, so you sort of, kind of have an idea of what a pointer is from CISC 124. So you know that in Java, Java has primitive types and reference types, right? If you remember 124, in 124, you should have been told that a reference is just a way, is just a mechanism that allows the computer to find an object in memory, right? Now, typically, often what's used is the memory address of the object, right? So if you know the memory address of an object, right, the computer can access that memory address, and get access to the object that's sitting there. So in C, a pointer literally stores a memory address. That's exactly what it stores, right? So a pointer references a location in memory, i.e. it stores a memory address, right? Okay, so if a pointer stores the memory address, you need a mechanism to get the value that's stored at that address, right? So the mechanism that's used to get the value pointed at by a pointer is called dereferencing the pointer, right? So pointer stores the address of an object. Dereferencing the pointer gives you the object itself, right? So an analogy here is that a page number in a book's index is a pointer, right? The page number in the index isn't the page itself, right? It just tells you where the page is located, right? So the page number in the index is a pointer, right? When you go to the page, that's like dereferencing the pointer. A similar analogy would be your house address, right? So you live at, I don't know, 1234 Liberty Lane or something like that, right? That address is not your house, right? But when you go to that address, you've gotten to the house, right? So your house address would be like a pointer, right? Your house itself is the object being pointed at. Okay, so what's the syntax for defining a pointer? So unfortunately in C, it's a little bit confusing. Right. Okay, so if you have, so a pointer looks like this. So if you have an object of type T, and you want to make a variable that is a pointer to an object of type T, your type becomes T star, right? It doesn't matter if the space is there or not, right? So you could also write it as T and then star right after the T. Okay. So here, that int star there indicates that the thing called PTR is a pointer to an int, right? So if you store an address in PTR, right, whatever is sitting at that memory address, the compiler will assume is an int object. Right? So in other words, on my computer, it's going to assume there's a 32-bit value sitting at that address that represents an int. Right? So PTR is a pointer object. It stores the address of an object type int. Right? Most programmers will say PTR is a pointer to int. Right? Now, as I said, unfortunately, there's no standard way of declaring the pointer. Right, so the space, whether or not there's a space in front of the star or not, doesn't matter to the compiler. So PTR1, PTR2, and PTR3, these are all pointers to int. Right? I'm always going to write it this way because this is the way that Linus Torvalds wants people to write it who develop for the Linux kernel. Many other programmers will write it this way. So int and then no space after the star. Right? The argument here is that the int star is all one word, so that looks like a pointer to int. You can also write it like this. So int star space star, right? The number of spaces doesn't matter. And so that's another way that you could write it. They all mean the same thing to the compiler. Pick one and stick with it. Right? Don't flip between them. Right? So this is what's used in the Linux kernel. This is what's used by probably most modern C programmers. This is what's used or is common in C++. Right? I'm always going to use the first one. All right, so you can store the value all caps null in a pointer variable. right? So the word all caps null is C's way of indicating no object, right? Java's way of indicating no object is lowercase null, right? They mean similar things in this context, right? So the value of null, the standard says, is equal to the numeric value of 0. So you can also use 0 in place of null, right? But null is easier to read, right? You also don't get confused on whether or not the variable is rather a numeric value or a pointer value. So int star ptr equals null means ptr points at nothing, right? If you try to use ptr for anything, so if you try to dereference ptr, you get undefined behavior. Right? Anything can happen. So there's no safe operations that you can do with null, right? With a null pointer. Right? So the only sensible thing that you can do with a null pointer is to test whether or not the pointer is null. Right? In C, there's no standard way to do this. There's multiple ways you can do this. Right? So you can use the not operator and write if not ptr, right? So if not ptr means ptr is a null pointer, right? You can check for equality to null directly, right? So if ptr equals null, then ptr is a null pointer. You can also check for equality to 0, but that's arguably less clear than using null, right? So any of these are acceptable. The first two would be preferable, and I guess most advanced C programmers would use the first. I would suggest you use the second in this course if you're not comfortable with pointers, and most of you won't be comfortable with pointers at this point in time. If you want to test if it's not null, you can just do the, I guess, opposite logical operation, right? So instead of if not ptr, you can write if ptr, right? And that means ptr is not null, right? In other words, ptr points at something, hopefully, right? You can also write if ptr is not equal to null, and you can compare it to 0, right? If ptr is not equal to 0, right? And so you might ask yourself, well, why does null exist? That's a good question, right? There is an argument to be made that null should not exist, right? You can't do anything safe with it anyway, so why does it exist, right? And so the reason that it exists is because the people who created the language thought it might be useful to indicate that there is the absence of an object. Right, that's basically what a null pointer is telling you, right? It points at nothing, therefore there is no object, right? And so the creators of the language argued that it may be useful, or thought it may be useful to indicate, to let the programmer have a way to indicate that there is no object. It turns out this has caused all sorts of bugs in code. One of the people who came up with this idea says that he regrets ever coming up with the idea of null. You can also, if you're going to use it for to indicate the absence of an object, if you have an array of objects, so if you have an array and the array is an array of pointers, you can use null to indicate the end of the array, right? Or to indicate that there are no more elements in the array. Right, and that's similar to how 0 is used to indicate the end of a string, right? So you have an array of car that's 100 characters long, but you can mark the end of the string anywhere in that array using the number 0, right? So similarly, if you have an array of pointers where you have that can store 100 pointers, somewhere in the middle of the array you can stick in null to indicate that there are no more pointers in this array, right? And so that is occasionally a useful thing to do. In the standard library, null pointers are often used to indicate an error condition, right? So you have a function that returns a pointer to something. If it returns null, that usually indicates that an error has occurred of some kind. Okay, so you generally want to avoid null pointers, right? And so what that means is that a pointer should always point at something, right? So a pointer should always refer to an object of some kind. All right, so a pointer stores the address of an object. So as a programmer, you need to know, how can I find the address of an object? So C has this operator called AND, not double AND, right? So there's a single AND for bitwise AND, right? There's a double AND for logical AND, and now there's another single AND that is the address of operator, right? So the address of operator is operates on one thing, right? The other two ands operate on two things, has two operands. So if you write and then a variable name, that gives you the address of the object stored in A, right? So here we have an int A, right? Its value is 99, right? If you want to make a pointer to the object A, right, you would write int star. You'd give your pointer a name, so PTR, right? And you could write address of A to indicate that PTR points to the object whose name is A. Right. So a pointer can store the address of any int. So it's completely legal to reassign that pointer to point at something else. Right? So here's A is 99, PTR points at the A, right? I've got B, that's 55, it's also an int, right? So I can make my pointer point at B, right? So pointer equals address of B, now it says that the pointer now points at B, right? And that's perfectly fine and probably a common thing to do in C. Right. Okay, so you now know how to initialize a pointer so that it points at something. Right? Now, how do you get the value that the pointer points at? Right? So in other words, if I have PTR at this point here, right, can I get to the object whose name is A? And the answer is yes. Right? The way you do that is you dereference the pointer. Again, C has made the unfortunate choice to use the star as the dereference operator. Right? So now the star means multiplication. Right? It also means you're making a pointer type. Right? And now it means you're dereferencing a pointer type. Exactly why they chose to do this or recycle the operators, I don't know. Right? But it can be confusing. So the pointer dereference operator star dereferences a pointer, gives you the object that the pointer is pointing at. Right? So here's A. Right? It's an int. Its value is 99. Right? I can make a pointer that points at the A. Right? So PTR is a pointer to int. Right? It stores the address of A, right? Okay, so star PTR, right? So you write the star in front of the pointer name, that dereferences the pointer. What does that do? It gives you the object that PTR is pointing at. So star PTR here literally means, is the same thing as writing A, right? So PTR points at A, star PTR is A, right? So this is A plus 1. Right, which is 99 plus 1, which is 100, so B becomes 100 in this case. Right, so A is 99 and B is 100. Right, so int star says so type star indicates a pointer type. Right, star variable indicates dereferencing the variable. Right, getting the object that the pointer points at. Right, so using pointer dereferencing, you can also assign a value to an object. Right, so in other words, given PTR, right, I can assign a value to A if I dereference the pointer. Right, so once again, A is 99, right? PTR is a pointer to an int, and it points at A, right? If I dereference the pointer, right, that's exactly, in this case, that's exactly like writing A, right? So A equals minus 33. Right? So if you print out A in this case, you get minus 33. Right? Okay, so remember, null is bad. You don't want to do anything with a null pointer. Right? So here, I've got a null pointer. Right? PTR points at nothing. I'm going to try to dereference it and assign a value. Right? So what does this do? Well, it goes, well, in this case, it's going to try to dereference a non-existing object. Right? So the object doesn't exist, so I'm going to try to assign minus 33 to some object that doesn't exist. What happens, so in this case, on my computer, it crashes the program. The language says that anything can happen here. So you may be in the situation where if you dereference a null pointer, your program doesn't crash and something else happens. I think that would be quite unusual on most computers. I think if you dereference a null pointer, it probably almost always crashes. But the language says that's not necessarily what happens. Right? It simply says undefined behavior results if a null pointer is dereferenced. So don't dereference a null pointer. If you're given a pointer and you don't know that it might be null, you have to check if it's null first before you dereference it. Void. So the language likes to recycle keywords and operators. So the language also recycles the keyword void. Right? Now remember, void in the parameter list means there are no parameters. Right? Void in front as the return type indicates that there is no return type. Void as a pointer type, so void star, means that this pointer can point at any kind of object. Right? So back here, PTR has type int star, so it can only point to an int. Is this going to work? Oh yeah, this doesn't work. I have to stick this inside of a main function. So here, we've got void star p. So that says that p can point at anything. Right? Well, that means you can store any memory address in p. Right? So in other words, I can make p point at the object x, which is an int. Right? On the next line, I can say p now points at the object y, which is a double. Right? And on the next line, I can say p points at the object str. Str happens to be an array of car. Right? So what this actually does is that p points at the first element of str. Right? So in other words, it points at the h in this case. That's not important right now, right? But it's legal to write. Right? So you can store any. Sorry, let me clear this. This looks awful. So. Okay, so you can store the address of anything in a void pointer. Now the problem is it's a void pointer, so anything, it could be pointing at anything. So what you're not allowed to do is that you're not allowed to dereference the void pointer directly. Right, so here we got x is 1, void star, right? So we have a void pointer. So p is allowed to point at anything, right? It can store any memory address. So I'm going to store the memory address of x, right? You're not allowed to dereference p directly like that. So if you run that, you're going to get a warning, right? Warning dereferencing a void pointer, and then you get an error. So in this case, it's a compilation error, right? Void value not ignored as it ought to be, right? Error dereference of a void pointer. All right, so you might say, well, void pointers don't seem very useful in this case, right? Yes, I can store anything in it, but I can never get the thing that's being pointed at. So that's not true, right? So if you want to get the thing pointed at, you have a void pointer, you want to get the thing pointed at, what you have to do is you have to take your pointer and you have to tell the compiler what is the type that's being pointed at, or what is the pointer type, right? So the way you do that is as follows, right? There's x, it's an int, p points at x, right? But its type is void star, so I can't dereference it directly, right? So I can't dereference p, right? But what I can do is I can tell the compiler, hey, p points at an int. So I can cast it to int star, right? Now that I've got a pointer to int, I can dereference that. So I can write star, round brackets, int star p, and that dereferences p, treating p as though it points at an int, right? If that's too confusing for you, you can stick in an intermediate pointer. Like that, right? So you can make a pointer to int called q, right? And you can tell the compiler, hey, treat p as though it were a pointer to int, right? And so now it can dereference q, right? Because it knows the type, right? That's the problem here. So you can't dereference p directly because the compiler doesn't know the type that p points at, right? So you can't determine what object is sitting here, p is pointing at. Right. But once you tell the compiler that p is pointing at an int, right, you can now dereference the pointer q, right? This is the exact same thing without creating the temporary variable q, right? And so this works just fine. You get y equals 1 here exactly as you'd expect. Right. So you might wonder why this void pointer exists in the language, and it turns out if you want to implement a generic type, a generic data type, which we haven't talked about if you're in 124. If you've taken 124, you should know what I'm talking about. You can use a void pointer to implement a generic type. Right? So for example, you can make a list in C where the elements of the list can be any objects, right? Just like in Python. All right, so what on earth are we going to use pointers for? So it turns out they're super useful. right? In Java, your references are probably implemented as pointers, right? In Python, your references are implemented as pointers, almost certainly, right? And it turns out there's lots of common programming problems that are easily solved if you have the ability to create a pointer. Right? Okay, so probably one of the most common problems is you have a function, right? And you want the function to change a variable that's owned by the caller of the function. Right? So here's swap. Right? Swap takes in two doubles, x and y, and it switches their values. Right? You know how to swap, right? You make a temporary, you assign the value to x, you assign y the original value of x, right? Kid stuff, right? Inside the function, if you print out the values of x and y, they will in fact be swapped, right? So here's my main function. I have a and b, right? Their values are 1.5 and 99.9. I would like to swap a and b by calling the function swap, right? Does it work? Okay, so before calling swap, a is 1.5 and b is 99. Inside swap, x and y in fact swap, right? X originally got the value from a, y originally got its value from b. Inside the function, they swap. After calling swap, a is still 1.5 and b is still 99. Right? This is exactly the way it works in C. This is exactly the way it works in Java. And if you wrote the same thing in Python, you would also get the same results, right? Using that version of swap, you can't actually swap the values of a and b, right? You can swap the values of x and y, but that's not the same thing. Do I tell you it? Yes, okay. So the reason this doesn't work in C or in Java is that calling a function in C is done by passing by value. So what that means is when you write swap AB, right, it's not a that's passed to the function, right? So in other words, the variable a is not passed to the function, right? It's the value of a that's passed to the function. So the function gets the value 1.5, right? And it stores that in x, right? If you pass in the b, the function doesn't get the variable b, right? It gets the value stored in b, right? So it gets the 99.9. This is why it's called pass by value, right? It gets the value, it doesn't get the object itself. So now x is 1.5, y is 99.9. Inside the function, you can swap x and y, right? But that x has no connection to this a, and that y has no connection to that b, right? So inside the main function, a and b do not switch their values. Okay, so what is the only way for swap to change the values of a and b, right? Well, it needs to get a and b, right? That's the only way this could possibly work, right? How do you give it a and b? Well, you give it a pointer to a and you give it a pointer to b, right? Inside the function, you can dereference the pointer. That gives you the underlying object a and the underlying object b, right? So the correct way to write swap in this case, right, is to not have a double value x, but rather a pointer to a pointer to a double value, right? And for y, you also have a pointer to a double value. When you call the function, right, so here's a and b, when you call the function, right, I need to give it a pointer to a double. So I pass in the address of a when I call the function, right? And when I need to give it a pointer to a double for its y, so I pass in the address of b, right? Now inside the function, right, swap now knows the address of a and the address of b. So it can now affect or change the underlying objects by dereferencing, right? So I want to create a temporary variable, right? I want to know what is the value stored in x, right? I want to remember that. So I dereference x, right? That gives me the double value stored in x, right? And we store that in temp, right? I now want to do the swap. So I want to store the value pointed at by y into the value pointed at by x, or the object pointed at by x, right? So dereference x, right? In this example, it gives me a, right? Store the value pointed at by y. In this example, it gives me 99.9, right? Dereference y, right? So in this example here, it gives me the variable b, right? and that stores the value of temp, which is 1.5, right? So now A and B switch, right? And when you run this version of swap, in fact, after calling swap, right, A and B have in fact switched values, right? So if you want a function to change the value of a variable owned by the caller, right, one solution is to give the function pointers to the objects rather than trying to get rather than the values of the objects, right? So here we want to change two double values here, so my function takes in two pointers to double values up here, right? Inside the function, you dereference the pointers to get the underlying objects, to manipulate the underlying objects. Okay, so there's another example of using a pointer as a function parameter, and that's if a function needs to return more than one value, right? And so C is like Java, you can only return one value from a C function, right? Python, you can return a tuple, which is nice. So if you want your function to return more than one value, one way to do this is to return one of the values, right? Any other values that you want to return, you can have the caller pass in a pointer to pointer to an object in which you can store the returned value, right? So here's max, right? Max of an array of int, right? So max returns the maximum value in the array A, but it also returns the index of the maximum value, right? The way that it returns the index is it requires the caller to provide us with an object of type size t. Right? Size t is the type that's used to represent indexes in C. Right? Right. Now I want the object itself because I want to write into that the caller's variable to store the index, or to tell the caller what is the index of the maximum value. Right? So I don't need an object of type size t. What I need is a pointer to an object of type size t. Right? If they give me a pointer, I can write into their variable, and now when they look at the variable after the function returns, they've got the index of the function of the maximum value. Right? So all of this stuff here is just max. Right? It's just finding the maximum value. Right? Before you return, you write in the index of the maximum value into index. Right? So how do you do that? Right? You dereference the variable. Right? That gives you the caller's object that can store the index. Right? And you store the value of I high, which is the index of the maximum element. We then return the maximum element on the next line. Right? So here's my array 63187 blah 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 blah. Right? I guess the maximum value is the 9. So it's at index 0, 1, 2, 3, 4, 5. Right? So if I run this program, hopefully I get the index is 5. Yes, max is 9, index is 5. Now, how do I call this function? So this is the tricky part here. Right? So, whoa, sorry, oh no, go away. Okay, so the function requires a pointer to a size t object, right? Now the common mistake here made by many new C programmers is that they say, okay, this function needs a pointer to a value, so I'm going to make a variable that's a pointer to a value. So they do this, like that, right? And they write that. Now, unfortunately, the compiler is perfectly happy with this, right? So the compiler says, okay, what is I? Well, I is a pointer to a size t object. What does max need? Well, it needs a pointer to a size t object. So it happily compiles this program, right? The problem is when you run it, oh, we got a problem, right? And it barfs down here. Right. Okay, so what's going on here? Right. So remember probably the second thing I told you in this notebook, right? If you have a pointer, it ought to point at something. Right? Here I've got a pointer. It's not pointing at anything. Right? I haven't assigned it a value. Right? I don't know what this pointer is pointing at. Right? So it points at, this is effectively pointing somewhere in memory, right? But it's not pointing, whatever it is, there's not actually a size t object there. Right? So what this function is really asking you for, it's asking for an object to write the answer into. And that means you need a size t object to write the answer into. Right? Here you've got a pointer to a size t object. You don't have the size t object. Right? So your options in this case are to either make an object like that, and then pass in the address of the object like that. Right? If you don't like that, you can do the following. Index, and now make a pointer to index. Right? And now pass in index. That would be fine. Sorry, pass in I. That would be fine. Right? But I would argue the easier thing to do in this case is to just go with I and take the address of I here. Right? All the alternatives work, right? However you're comfortable writing it, write it that way. Right? Oh, actually, there's the next part actually shows you the error here, right? So that's the common error, right? The programmer says, oh, I need a pointer, so they make a pointer, right? Not recognizing the fact that what they actually need is an object to point at, right? That's really what you need here. All right, I'm going to call it quits there. I got something to do before 1:24 in an hour, so I have to go and get that done. We'll finish off this discussion from this point in the next lecture.